So maybe I can talk about why I actually got into this business of almost minimizers to begin with. And as Hugo mentioned, I have been working on free boundaries for quite a long time. And I was in Germany for a postdoc. And when I came back to the United States, I actually came to the state of Washington, where this picture actually I took from my background is actually from a mountain around here. And when I came, I worked with Tatiana Toro, who's one of my collaborators in this project. And she was interested in understanding what happens if you have an energy and you don't look at minimizers of this energy, but almost minimizers. And this also gives rise to free boundaries, which is, something I'm very interested in understanding. However, before getting into this almost minimizer business, I think I will start with the minimizers themselves so we can actually compare what can be done in comparison with the minimizers. So let's see here. Let me start with a problem that I think many of you really likely know, and that is going to be the Alt-Caffarelli-Friedman functional. So let's look at the minimizing problem. Here we have a domain, let's say in Rn, that is bounded, connected, let's say Lipschitz. I am going to have two functions, q plus and minus, which are in L infinity. And my set of admissible functions, I'm going to call k. So this is going to be the collection of functions in L1 log for which the gradient is in L2. And that's because I want to be able to integrate the gradient there squared. So the minimizing problem we have is given a boundary data U0, which lives in our set of admissible functions, I want to minimize this energy here, which if you see, so includes the gradient squared, but also includes that function q plus squared, where our function u, the minimizer, is greater than 0, and q minus squared, where u is less than or equal to 0. And we want to minimize this energy among all functions in our admissible set, which coincide with u0 on the boundary of the domain. So this is related to many other problems we can think of that come from PDE, which are actually, minimizers of an energy. In the case in which this function q minus, the one that appears in the negativity set, let's say, or where u is 0, when that function is 0, and when we also assume that our boundary data is greater or equal than 0, we have what we call the one-phase problem, and we usually refer to this energy as the Alt-Caffarelli energy. And when q minus is not assumed to be 0, and we don't have this sign restriction on u minus, on u0, sorry, we have the so-called two-phase problem. That's the general problem, and we refer to this energy as the Alt-Caffarelli-Friedman energy. So with respect to minimizers, in the case of one phase, Alt and Caffarelli were able to show using, the standard methods of calculus of variations, we do have minimizers for the one phase. Okay, what else can we say about these minimizers? So first of all, of course, you start with a minimization problem. You want to understand what are the equations that this minimizer satisfies. So you can show that in the case of the one phase problem, because our boundary data was assumed to be greater or equal than 0, our minimizer will be greater or equal than 0. Very importantly, it will be subharmonic in the whole domain, and it will be harmonic in the set in which the function is strictly greater than 0. And that also plays a very important role when we are proving things about the regularity of the minimizer, which we'll come back to when I'm talking about the almost minimizers. With respect to the regularity, as I mentioned, that we are going to be interested in, you can show that if you have a minimizer of the one-phase problem, this is going to be locally Lipschitz, which is the optimal regularity that you expect across. Finally, you can show that if your function q plus is bounded away from 0, let's say with a bound c plus, then if you pick a point on the positivity set, if you look at the quotient between u and the distance between x and the free boundary here is the boundary where u is greater than 0. This is approximately 1. What this is telling us truly is that as you approach the free boundary, you grow like the distance to the free boundary. And we can also show that the positivity set, where u is positive, this is of locally finite perimeter, and our free boundary is n-1 rectifiable. So you can say things about regularity of the minimizer and also things about the free boundary. We are going to come back to the free boundary and say more things about it. With respect to the two-phase problem, so when we have the Q plus and the Q minus, so we have the two portions on the energy and we don't have the requirement that the boundary data is positive, you can also show that there are minimizers, so the minimizer exists, and you can show that, like in the case of the one-phase problem, here you have the U plus and U minus, the positivity and negativity part of U, they are subharmonic, and the Laplacian is equal to 0, both in the positivity set and in the negativity set. So this is, again, something that turns out to be quite important also when you're trying to prove the regularity of the minimizers. As in the case of the one-phase problem, you can prove that a minimizer has to be locally Lipschitz. And once more, now assuming that both Q plus and Q minus are bounded away from 0, if you pick a point either on the positivity set or negativity set, then as you approach the free boundary, you grow like the distance to the free boundary. And both the positivity set and the negativity set are sets of locally finite perimeter, which is what we expected from the one-phase problem as well. With respect to the free boundary, we definitely want to say more than what we have so far. So in the case of the one-phase problem, our function has a sign, our minimizer. So here, the free boundary is the boundary of the set where U is strictly greater than 0. And we can say many things, actually. So assuming that the function Q plus is Holder continuous and bounded away from 0 in dimensions 2, 3, and 4, you can say that the free boundary is actually a C1 beta n-1 dimensional manifold. So this is telling us that we do not have singular points. This is as nice as we want. In dimensions 5 or more, we have a dichotomy. So we can write the free boundary as a regular set, that's the one I'm calling R, which is a C1 beta n-1 dimensional submanifold, and a singular set, which I'm calling S here. And we can say some things about the singular set. We can say it is a closed set, and it has Hausdorff dimension less than or equal to n-5. And I will come back a little bit to this and say some people who have been doing contributions on these problems, just to mention some of the important literature. With respect to the two-phase, our function, our minimizer, can be positive and negative, so the free boundary has these two portions, okay? So the boundary of the set where U is positive and the boundary of the set where U is negative. And once more, assuming that now the functions Q plus and minus are Holder and bounded away from 0, you also need a requirement between which one of them is larger. Okay, this is a technical issue. In dimensions 2, 3, or 4, once more, our free boundary is a C1 beta n-1 dimensional submanifold, which is awesome. That's what we want. Those are the regular points. And then in dimensions 5 or more, we have the dichotomy of a regular set and a singular set. Once more, the regular set is C1 beta and the singular set is closed and with Hausdorff dimension n less than or equal than n-5. So I will be a little bit more precise here to mention a little bit who did what in this respect, and I will mention an important counterexample that was found. So with respect to the one-phase problem, we have, of course, the seminal work of Alt-Caffarelli in dimension 2, and then in dimensions 3 or more, there has been more people that have worked on this problem, so forgive me for just mentioning some. I will come back to a more recent work as well. But we have the work of Alt-Caffarelli, we have Caffarelli, Jerison, and Koenig, Weiss, and we also have Jerison and Savin. And for the two-phase problem, once more, we have now Alt-Caffarelli-Friedman, then the works of Caffarelli, Jerison, and Koenig, Weiss, and Jerison and Savin. And let me mention here, so in dimension 3, Caffarelli, Jerison, and Koenig were able to use this Weiss monotonicity formula to show that we do not have singular points in dimension 3. Jerison and Savin were able to use that and other techniques to show that in dimension 4, we do not have singular points. And then there is this very interesting result by De Silva and Jerison that shows that there exists a non-smooth minimizer for our two-phase energy in R7, for which the free boundary is a cone. That is to say, we do have then singular points. So those might happen for dimension 7 or more. And this is, let's say, the cousin of Simon's cone, if we will. Of course, this leaves open the question of what happens in dimensions 5 or 6, and do we have singular points there or not? So very interesting problem to consider. This is telling us many things. So now we have been able to discuss the regularity of minimizers and the regularity of free boundary with still some open questions, but still we were able to say many things. Let me mention a more recent work that has come up from the Philippis, Spolauer, and Velishkov, in which they consider this energy here. So they have the set where U is positive, the set where U is negative, and they have been very interested in understanding these two-phase points. So a point on the free boundary is going to be called two-phase if it is both in the free boundary of the positivity part and the negativity part. So it really lives at the interface of both phases. And they were able to show that for the two-phase points, there is a small radius, so that if you look in a neighborhood of that point, the free boundary for both the positivity phase and the negativity phase are going to be C1 eta graphs. Their energy is slightly different from the energy of Alt-Caffarelli-Friedman. However, this is a little bit more general. So if you have a minimizer of the Alt-Caffarelli-Friedman, you can actually rewrite it as a minimizer of this energy. So this includes that case. Let me tell you a little bit more, some other things they have done in this more recent paper. So still considering a local minimizer of this energy, they were able to prove the dichotomy we expected for both the positive part of the free boundary and the negative. That is to say, we can write the free boundary as a regular part and a singular part. And here the statement I'm writing is for the positive part of the free boundary, but a similar one holds for the negative part. So they were able to show that the regular part, as we wanted, is relatively open, and it is locally C1 eta for some eta positive. Also, very importantly, the two-phase free boundary is always made of regular points. That's really important. The singular set, as we expected, is a closed subset of Hausdorff dimension at most n-5. And there is this, let's say, threshold dimension n star, which we know is between 5 and 7, for which if our dimension, our universe, is in a dimension less than this threshold, there are no singular points. The singular set is empty. If we are at a dimension exactly equal to this threshold dimension, then the singular set will be locally finite. And finally, if our dimension is larger, then the singular set will be a closed rectifiable subset. And here the dimension is n minus n star with locally finite Hausdorff measure of dimension n minus n star. So this is, again, what we expected with the looking at the previous results. So now let me discuss a little bit with you, what are these almost minimizers? What can we say about them? And here there has been a surge of interest in almost minimizers in the recent years. So there's lots of people doing different work connected to almost minimizers. So I will also tell you some differences between the types of almost minimizers people have been looking at. So once more, let's start with the one-phase problem. So here we have our domain as before, bounded, connected, let's say Lipschitz. I'm going to have that function Q plus, let's say in L infinity, and our set of admissible functions are going to be functions in L1 log, which are greater or equal than 0 almost everywhere, for which the gradient is in L2 log. Now, what is the definition of this almost minimizer? So I'm going to start by including this kappa alpha, and we're going to see that this appears in the definition. And I will also say that I have a multiplicative almost minimizer, because what has to happen is the following. I need to be able to compare the energy of my candidate, U, almost minimizer, with the energy of any other function for which, let's say this function V is defined in a ball inside of my domain and coincides with U on that ball. So if I didn't have this term plus kappa r to the alpha, if this were true, I would say that my U is a local minimizer. So because I'm allowing myself to have an error, and this error depends on the radius of the ball in which I'm comparing the two energies, we say that this is an almost minimizer. And because the term here is a multiplicative term, we call this a multiplicative almost minimizer. So here, just to remind you, the energy for the one phase problem is the gradient squared plus this Q plus term where the function is positive. So we need to be able to compare the energy of our candidate with the energy of any other function that is defined on a ball inside of the domain and coincides with you on the boundary of that ball. So here we have a multiplicative almost minimizer. For the two phase, we have a very similar setting, except we don't have to require our set of admissible functions to be made of functions that are greater or equal than 0. And the energy itself includes that other term that has Q minus squared where the function is negative. But the rest is absolutely the same. So keep in mind, we are not requiring that the energies are directly comparable with less than or equal. We allow ourselves to have this error that depends on the radius of the ball. So let's discuss a little bit what we can say about these almost minimizers initially in that setting. That's the first one that has been considered. So in 2014, Tatiana started looking at this problem, and they were able to show that if you have an almost minimizer with that definition, then this almost minimizer has to be continuous. And they were able to show an estimate of this kind. So if you are in a large ball inside of your domain, then in a smaller ball, you can compare u of x with u of y with an estimate of this format, which is what you need to show continuity. Well, that sounds really natural, but let's consider what are the stumbling blocks, or what are the challenges here that you have when you're thinking about almost minimizers. So the problem is, I think all of you, probably as we love our PDEs. And we really like the fact that if you have a minimizing problem, you can extract the Euler-Lagrange equation so you know what PDE this function is going to satisfy. Here, because we have that inequality with an error, our almost minimizers do not satisfy a PDE, which is a huge problem. We are also not going to have a direct free boundary condition as we had in the case of minimizers, which means that we have to just work really, really hard with these comparison functions. We only have the inequality, so we have to be smart about which competitors to choose and be very careful about the information we can extract out of those competitors. So let me tell you a little bit the idea of this one result. So I'm not going to have a lot of proofs, not to be too technical to talk, but I do want to discuss this one. The reason for that is one has to work much harder to get more information, but the general idea is based on this. We have to work really hard with the competitors. So we have to use competitors, and we have to iterate these kinds of estimates to be able to obtain regularity for the almost minimizers. So if we think about this, I'm trying to show that my almost minimizer is continuous. And actually, let's get ahead of ourselves a little bit. If we think about our end goal in life here with the almost minimizers, let's remember that minimizers were locally Lipschitz. Almost minimizers, we expect them to be up to first order of the same regularity as the minimizers. So truly, I'm hoping within myself that I can show that my almost minimizer is Lipschitz, which means that I truly want to estimate something about the gradient. And that's why this function omega in red here is so important. This is the crucial, let's say, term that we want to bound to be able to say something about the almost minimizer. So we start with our almost minimizer. Let's say we have a ball centered at x of radius r inside of the domain. And we look at our function ur star. That is a function that solves Laplace's equation in the ball with boundary data u, the almost minimizer, on the boundary of the ball. Now here, this is fantastic because, well, ur star does solve a PDE, so I have a lot of information about it. In particular, its gradient squared is subharmonic, which happens to be quite important. So if we think about this omega function in red, okay, let's do the simple thing, add and subtract the gradient of ur star squared. So this appears here in the first line. For the second line, we use the fact that here the radius s is smaller than r, fantastic. Then I use the fact for the second term that the gradient of ur star is subharmonic. That is why I can go from that first integral on a ball of radius s to the ball of radius r. I am already very happy with the second term, but I do want to work harder on the first term. So I'm going to flip the page and work harder on this first term a little bit. So I copy the first term. I remind myself that UR star is a beautiful harmonic function. That means that it minimizes the Dirichlet energy. If I look at any other function with the same boundary data, in particular U. So because of that, I'm able to rewrite that first term as this difference, which is really nice because now I can estimate the first term. That's where I have this red inequality with this other term because U is an almost minimizer. And then I have some errors that pop up, but that is totally okay. I copy my second term and then I have this error that shows up. Then, okay, I can cancel a few things and I land at the end with using once more the fact that UR star is a harmonic function on the ball, so minimizes the energy. So I'm able to compare that initial term with this estimate and notice that this integral that I'm left with is truly connected to that omega term that I had on the previous slide. Except I don't have the average integral and I don't have the square root, but that is easily fixable. So putting everything together, I can estimate the omega term, which is an average of the gradient on a ball of radius S, in terms of that average on a slightly larger ball of radius R. So you can see that we're going to iterate this result, use a dyadic argument. So iterating it, we are able to say that we can compare that average of the gradient on a smaller ball with the average of the gradient on a bigger ball plus a logarithmic term. And this is exactly what we needed to obtain that estimate and prove continuity of our almost minimizers. So of course, I'm skipping a lot of details, but this is the crux of the idea. However, we wanted to show more. So in the case of almost minimizers, again, in that simple, that starting context, let's say, Guy and Tatiana were able to work a little harder and show that the almost minimizers, they are actually locally Lipschitz, but initially you can only show that away from the free boundary. Then you can show that away from the free boundary once more, you are actually C1 beta. And the proofs of these results follow the same ideas that I showed you before, but you have to be a little bit more careful because you are trying to get more information, of course, but the idea is the same. Okay, however, if we go back to the minimizers, thinking about Alt-Caffarelli and Alt-Caffarelli-Friedman, we knew that minimizers were locally Lipschitz. So this is what we want out of the almost minimizers. And if we remember the proof of Alt-Caffarelli-Friedman, the ingredients of this proof of the Lipschitz regularity included the subharmonicity of U plus and minus, which we do not have. They also included the fact, it's very important in the proof, that U is harmonic in the positivity and negativity phase, which we also do not have. And for the two phase, we actually needed to work a little bit harder to get the Lipschitz regularity, and we needed an Alt-Caffarelli-Friedman monotonicity formula. That is because when the function is allowed to be positive and negative, we need to be a little bit more careful with what happens with the interplay of these, the two phases. So for that, the Alt-Caffarelli-Friedman comes into play. Okay, can we still get this for the almost minimizers? And the answer is yes. We are able to show that the almost minimizers are going to be Lipschitz. However, we do not have at our disposal either one of these initially. So we don't have the PDEs. We initially didn't have an Alt-Caffarelli-Friedman. However, Guy and Tatiana were able to once more play and be very, very careful with the fact that we do have competitors that we can use to our advantage. And these competitors might solve PDEs, allowing us to compare things in a nice way. And you just have to be really, really careful with the error terms that you have. So the quantities that play an important role here are the average of U on spheres, the average of the absolute value of U on spheres, and our old friend, omega. That's the one that we really are interested in. However, in the case of the two phase, they also needed a version of the Alt-Caffarelli-Friedman monotonicity formula, because you also run into this issue that you need to compare the two phases in a careful way. So let me just briefly mention more or less, let's say a very brief sketch of the proof. So here, let me remind you, let me go back here for a second. Omega, that's the last quantity, that's our friend, that's the one I really want to estimate. M is the average of U on spheres, and then there is this other quantity, which is the average of absolute value. So the important kind of setting, what we need to be careful is what is the relationship between omega, the one I want, and m. So you have to separate it into cases depending on which one is large and which one is small. For the first case, omega is large and m is also large. For the second case, omega is large and m is small. And for the third case, omega is small. And we're going to see that one of these cases is fantastic. It will even give us better regularity than we need, let's say. And the two other cases are the ones that are going to give us exactly the Lipschitz. So in case one, in which both omega and m are large, we are actually able to show more. This is the good case. We are actually able to show that u is actually going to be C1 beta in a small ball, and the gradient, the supremum of the gradient will be bounded like omega. So this is what we wanted. This is the best possible case. We have C1 beta regularity if case one happens. For cases 2 and 3, so case 2 was the case in which omega is large, but m is small, and case 3 is the case in which omega itself is small. What we have to do is look at this radii made by a fixed radii divided by 3 to the k, and we have to check if at any point the pair made of that fixed point x with those radii, if that ever satisfies case 1. Case 1 was the good case. If it ever satisfies case 1, we are good. Then we have that we are C1 beta. If only cases 2 or 3 occur, then we can show that the lim sup of omega is bounded. And that allows us to conclude that if x is a Lebesgue point of the gradient, then the gradient will be bounded approximately by that constant, which is what is going to give us the Lipschitz regularity. In the case of the two-phase problem, as I mentioned, we do have to be a little bit more careful because the function is not allowed to be positive or negative. So we need to study the interplay between these relationships in a more careful way. And this is where a version of the Alt-Caffarelli-Friedman monotonicity formula comes into play. So here, what Tatiana and Guy were able to show in that context was that we have an almost monotonicity formula. So it's not a monotonicity formula as before. We do have this extra error term that is additive. However, this is truly not a problem. This allows us to obtain what we needed. So we need to control the oscillations on small intervals, and that is good enough for that purpose. So this also settles the question for the two-phase. With respect to the free boundary, we usually go for the regularity of the minimizers or almost minimizers, and then we discuss the free boundary. Assuming we have an almost minimizer for the one phase with a function q plus that is in L infinity and continues, also bounded away from zero, Guy and Tatiana were able to show that you have non-degeneracy. This is usually very important if we think about free boundaries. Many times you want to pick a point on the free boundary. So here the free boundary is the boundary of the set where you is positive, and you want to do a zooming in procedure. And you hope that by doing this zooming in procedure by a rescaling of your function, you obtain another function that is a solution of your problem. And hopefully that one is a little easier to either classify or have information about. And you want to have information from the initial function, let's say, out of this. But for that process to work, it's really important that you have non-degeneracy so you don't go to zero too fast. And here we also have a non-degeneracy for our almost minimizers. And once more, you can say, how are you growing as you approach the free boundary? So here, looking at this estimate in red. With respect to the structure of the free boundary, again, talking about the one phase case first, and assuming that the function q plus is continuous and bounded away from zero, they were able to show that the positivity set is locally non-tangentially accessible. So here you have to satisfy a corkscrew condition on the set and on the complement, and also a Harnack chain condition. They were also able to show that there is an Alfors regular measure that is supported on the free boundary here in a small region of the free boundary. The free boundary is n-1 uniformly rectifiable, and the positivity set is locally of finite perimeter. With respect to the two-phase, things become much more complicated. So assuming that our two functions q plus and minus are continuous in L infinity and bounded away from zero, the free boundary is locally Alfors regular and uniformly rectifiable. And here for the one phase case, assuming that our function q plus is holder and bounded away from zero. So for a one-phase problem, we have the dichotomy that the free boundary is a regular set that is C1 beta and a singular set which is closed with HM minus one measure 0. And furthermore, you can show that the singular set does not appear in dimensions 2, 3, and 4, like in the case of minimizers. But notice that here the situation is much more complicated. This was done for the one-phase problem only. And this is a collaboration between them and Max. They were also able to say more. So here, K star is our, let's say, threshold dimension as before. That's the smallest natural number for which we have a stable, one homogeneous, globally defined minimizer, which is not a half-plane solution. And if we think about the works of Caffarelli, Jerison, and Koenig, Jerison and Savin, and the Silva and Savin, we do know that this dimension is between 4 and 7. So they were able to show that if our Q plus function is holder, bounded away from 0, if you have a number S larger than our dimension minus the critical dimension, then the HS measure of the singular set will be 0. So as we expected, take into account the information we have about that threshold dimension. Now, let me tell you something that I have been very interested in various problems. So what happens with a version of this for variable coefficients? And I want to mention that if we look at almost minimizers for functionals of the type Alt-Caffarelli or Alt-Caffarelli-Friedman, this actually shows up if you look at measure penalized minimization problems, for example, for Dirichlet eigenvalues of elliptic operators. And I will mention in the next few slides a little bit of several pieces of work, several papers that deal with related problems that involve variable coefficients. And I will give a reference for this example as well. So this actually is that. So if we look at the Laplace-Beltrami operator on a manifold, this is a paper of Lambolet and Sigbaldi on the existence and regularity of Faber-Crum minimizers from 2019. For example, this is a setting in which this gives rise to an almost minimizer, to a function of our type in which we have variable coefficients. Other examples of related work, starting with the seminal work of Caffarelli in '88, we have regularity for solutions to free boundary problems for uniform elliptic operators with C alpha coefficients. Then there is a paper in 2010 of De Quiroz Tavares, and here I'm going to mention papers that are really more connected to the one that I'm describing today. So here they assume that they have a matrix with holder coefficients. And what they were able to prove is looking at this energy that they have over there. They look at almost minimizers of this energy of multiplicative type. That's the one that I discussed earlier. So the same definition. And they were able to prove that these almost minimizers are regular away from the free boundary. So it was not possible for them to get at the free boundary to get the Lipschitz regularity. But they did show the Lipschitz regularity away. Then there is an interesting paper of Spolowor-Trey and Velishkov from 2019, in which they are interested, so their point of view is different. They're interested in the free boundary regularity. They have a multi-phase shape optimization problem, and what they do is they use an epiperimetric inequality to prove free boundary regularity for almost minimizers of the functions that I have been discussing with you in dimension 2. Here they had to restrict themselves to dimension 2 because the epiperimetric inequality they used was only done for, they did for dimension 2. However, I want to mention, so their point of view is different because they assume a priori that the almost minimizers are Lipschitz, and with that information, they are able to say something about the free boundary. In our work, we were interested in showing this Lipschitz regularity, so a different, let's say, perspective looking at it. Then we have this paper of Lambolet and Sigbaldi in which they look at first Dirichlet eigenvalues for the Laplace-Beltrami operator with volume constraint. This gives rise to almost minimizers with variable coefficients. Then there is this paper of Guy, Max, Tatiana, and I. And in this paper, we are interested in the regularity up to and across the free boundary for these additive almost minimizers. And I'll mention to you what's the difference between the multiplicative and additive almost minimizers, how do these relate, and so on. And this is part of a larger project that we have been working on. So this is one piece connected to the variable coefficients. Then there is also a paper of Trey from 2019 in which they prove Lipschitz continuity for eigenfunctions on optimal sets for functionals with variable coefficients. Their results are really connected to ours, but it's very interesting because neither ours imply theirs, neither theirs imply ours. So it's just connected work. And let me maybe compare and tell you a little bit more about all of these papers that are discussing almost minimizers. So initially there was the De Queiroz-Tavares. Our definition of almost minimizers is slightly different than theirs, but includes theirs. We prove Lipschitz regularity up to and across the free boundary in contrast to the work of De Queiroz-Tavares. In the paper of Spolowar, Trey, and Velishkov, they assume that our almost minimizers are a priori Lipschitz because their goal is to show what is the regularity of the free boundary. We show that this assumption is not needed, as we can prove that they are Lipschitz. And the class of almost minimizers considered in their paper doesn't look like it's the same as ours, but it is equivalent. So let me tell you what we actually have done and what is our definition of almost minimizers. So here I'm going to have, as before, a set omega in Rn that is bounded in dimension n greater or equal than 2. And our goal will be to study the regularity of almost minimizers of this energy. So here the difference with the energy that we had before is there is the presence of this matrix A. So when A is the identity, we are back into the original set. Our assumptions are going to be that Q plus and minus are in L infinity. Our matrix A is going to be assumed to be Holder continuous. I will assume that it is symmetric and uniformly elliptic. And let's see what we can do here. First of all, there is an initial challenge that is very natural, but somewhat unpleasant. That is, it is not, to be honest, it is not clear which definition is the best one to even define what is an almost minimizer when you have variable coefficients. I have another paper in which I have been looking at almost minimizers for a Signorini problem with variable coefficients. And once more, it's very interesting to actually realize that each definition brings up its problems later on. So in this case, we worked with two definitions. Let me start with the first one. So here I'm going to look at the one-phase problem, and I have this subscript B to remind us that this is the definition that involves balls. So our set of admissible functions are in L1 log with gradient in L2. And then we have for the one phase, the admissible set has to be of functions that are greater or equal than 0. I'm also going to have a kappa as before between 0 and infinity, an alpha between 0 and 1. And here I'm going to say that I have a kappa alpha additive almost minimizer if my function is in the set of admissible functions for the one phase problem, and I have an inequality, but notice here that my error term is not multiplicative anymore. I'm not multiplying it by our J energy. I'm adding it. So because of that, I call this an additive almost minimizer. And I have a picture here maybe to help us. So I know there's a lot of formulas in this page, but the idea is simple. You have your domain, pick a ball inside of your domain, which is completely inside of the domain. If you have any other function V that is equal to your candidate U on the boundary of that ball, you need to be able to compare the energies. So the energy of the almost minimizer has to be less than or equal than the energy of the other function, plus this error that depends on the radius of the ball. So that is why we have the additive almost minimizers. And here the energy for the one phase problem is the one that does not include the set where our function is less than or equal to 0. So here we are. Then we're going to have a similar definition for almost minimizers for the two-phase problem, additive almost minimizers. So same idea, we have this estimate between the energy of our candidate almost minimizer, the energy of this competitor V, and we have this error term that is additive in fashion. And here our energy is actually this one below because we are looking at the two-phase problem now. Okay, so these two definitions are of additive almost minimizers for the one and two phase problems with respect to balls. Let me tell you how these compare with our multiplicative almost minimizers from before. So I just copied here the two definitions so we can look at it. we can actually prove that multiplicative almost minimizers are additive almost minimizers. And that means that our definition includes the one that was used before by Guy and Tatiana, and also by De Queiroz and Tavares. And this is not, it looks, I'm going to say, maybe I'm allowed, I can say that, I think it looks pretty natural to assume that the multiplicative are going to be additive. There is a little bit of work that goes into that. And one has to show an estimate of this type that appears at the bottom for us to be able to show that if we are multiplicative, we are additive as well. So with that in mind, it looks natural that we should actually work with the additive minimizers instead. However, there's also the issue that we have the variable coefficients. And for all of you, I think it's very natural to see that we are going to do a change of variables at some point. So all of these balls from our definitions are going to be transformed into ellipses by this transformation. There is a little bit of another issue that appears when we are working with lots of free boundary problems that involve variable coefficients. And that is when we're thinking about the regularity of the function. In this case, it's an almost minimizer, but even if you're thinking about minimizers, at some point, you're going to have an assumption that at 0, for example, your matrix is the identity. And then if you're just interested in what happens around 1 point, what you do is you translate. So you assume that at that point, the matrix is the identity. That becomes a hassle and a problem sometimes that is significant when you're trying to prove regularity of the free boundary instead, because you need to have estimates for distinct points of the free boundary in the same neighborhood. So because of that, we need to do a change of variables that allows us to say that for this new matrix, we are still going to be the identity at the point that we want. So that's why we have to change our matrix in a special way as well. So here the TX transformation is the one that we would expect with this appropriate choice of the matrix. Then I'm calling E our ellipses that are transformed from the balls. I have a new function UX out of U. Q, the functions Q, of course, are going to change. And now the matrix changes in a certain way so that I can preserve this property that I want of being the identity at a given point. And in this context, having changed the variables, we have the set of admissible functions for which we are going to compare ourselves with the energy of other competitors over ellipses instead of balls. So here, this other definition is for almost minimizers of the one-phase problem with the subscript E, in which that means that we're thinking about ellipses. So I have a kappa alpha additive almost minimizer if I have this comparison between the energies, and I have an additive comparison. So my error is additive depending on the radius of the ball. And that has to be done for any ellipse inside of my domain and any competitor that in that ellipse, at the boundary of the ellipse, coincides with our candidate for almost minimizer U. So this is the definition for the almost minimizers that are additive on ellipses for the one-phase problem. We have a very similar definition for the two-phase problem, except the energy has this other portion. And with these, we wanted to see what we could do. What results could we actually stretch? What were the problems we were going to face? So let me mention a little bit what are the comparisons between all of these definitions. In the identity case, so when the matrix A is always the identity, that means we were in the original setting. And the two definitions between balls and ellipses, they don't change, of course, they're the same. Then if we have an additive almost minimizer with the definition of balls, you can show that you will be an additive almost minimizer with the definition of ellipses. The constants change, but an important comment is that they change in a universal fashion, so that is not a problem. Reciprocally, if you are an additive almost minimizer with respect to ellipses, you will be an additive almost minimizer with respect to balls. And once more, the constants change, but in a uniform fashion, universal fashion. And lastly, what I mentioned, we are actually able to show that if you have multiplicative, you have additive. So that means that really we should probably work with these additive almost minimizers and use as needed either balls or ellipses. So this is what we're going to do most of the times, working with the ellipses. So we had this kappa alpha almost minimizer with respect to our either one-phase problem or two-phase problem. And we just have to be careful and make this first observation, that is, if I have a symmetric uniform elliptic matrix, and I change my variables and create this new function U out of the change of variables with a new energy, with new matrices, new domain, and so on, am I still an almost minimizer? Because of course we have something like this for minimizers. Can we still say this for almost? We can, and we are going to apply this result many, many times, where the matrix S is the square root of our matrix evaluated at a point x0 on the free boundary, around which we are trying to understand what happens. So the results we were able to show were, first of all, we were able to show that our almost minimizers are additive almost minimizers with the variable coefficients. They are continuous. We were able to show that we are actually Lipschitz, first away from the free boundary. Then we were able to show that we are C1 beta with a beta that depends on the dimension n and on the alpha that appears from our error. And then we were able to show, first of all, that for the one-phase problem, we are locally Lipschitz. And let me mention that here we did follow the, let's say, the general ideas introduced by Guy and Tatiana, but we had really significant challenges because of the variable coefficients. If we think about this, maybe, okay, I don't know if that is fair to say, but in almost minimizers, the problem is that because we have so much less to work with, the error estimates are just so much more important. And once you introduce the variable coefficients, the error estimates become really significantly more problematic. And that is why here we had a lot of problems, especially when we were looking at estimates depending on different points. But for the one-phase problem, we were able to close that. That worked out. Let me mention a little bit here. In the case of the identity, our crucial estimate that I mentioned briefly in this talk was we needed to estimate this average of the gradient squared, because we're trying to show that our almost minimizer is Lipschitz. And the estimate we obtained that was crucial was this one in green. So here, in the context of almost minimizers for variable coefficients, if we have an ellipse inside of our domain, and at that point X, our matrix is the identity, we can actually follow the same procedure without so much pain and prove this directly. The problem is when the matrix is not the identity. At that point, we do a change of variables. That one, the new function is going to be an almost minimizer for different functionals and so on, but we can apply this to that. Now, the problem is for continuity. We need to compare estimates for different points, and this is where things become really hairy and more complicated. Then, of course, at the end, we have to compare the balls and ellipses, but that part is really trivial. In the case of the two-phase problem, we did face a similar issue that had happened in the Alt-Caffarelli-Friedman, and that is we needed more, because we needed to understand what is the interplay between the two phases of U if we are at the free boundary point for which we have the two phases. So here we also needed to prove some version of this Alt-Caffarelli-Friedman type monotonicity formula for the two-phase problem. And once more, we were able to prove this for almost minimizers. We didn't obtain a true monotonicity formula, let's say, but we obtained an almost monotonicity formula. And that was, so that's the one that appears at the end. That is not quite the same that Alt-Caffarelli-Friedman had, but that wouldn't be expected because we don't have minimizers. But the format of our error, which is this R to the delta, for a delta that we can somewhat control depending on our dimension and on alpha, which was the power coming from our error term, was enough for us to be able to estimate or be able to control the oscillations of our functions in small intervals, and allows us to prove that in the two-phase case, we also have Lipschitz regularity. So thank you so much.
Thank you very much, Mariana, for this very clear and interesting talk. So we can...
Thank you so much.
So I have a question